don't see it. Oh, there we go. And good afternoon. How are you doing? This is Meteorologist Paul Mireles. Thanks for joining me today on Cloudy with a Chance for Learning. We're going to talk about tornadoes. And, you know, I don't know if I'm the best teacher, but we're going to do the best we can, all right? So how are you doing? Have you noticed something outside? Have you noticed that we've got a little bit more sunshine? We had a little warm front that's come through. Temperatures north of the warm front in the 70s, but now we're breaking out into the 80s, and it's going to be pretty warm and breezy this afternoon. But we'll get to the forecast here in just a minute. Of course, we are here to talk about tornadoes and how they develop and where they come from and all kinds of details like that. So first of all, I just want to say hi. Turn down my volume here. Sierra, how are you doing? Chrissy, how are you? Julie, how are you doing this morning? Olga, Sylvia. Not this morning, this afternoon. I'm the morning guy. I wake up at 1:30, so everything to me is morning. Of course, we're in the afternoon. And Adriana, hi, how are you? Okay, so the first thing that we're going to do is talk about these tornadoes and how they form. Now, most of the time, see, there's two different things about tornadoes and how they develop. Probably the most common way is through what we call a supercell thunderstorm, and you have a lot of dynamics in place, and you have the tornadoes that develop from these very severe thunderstorms. There's also another way, and it's kind of like the way a waterspout is formed, and we're going to talk about that as well. And you'll have a landspout, okay, that kind of develops. And then really there's another way too, and that's a GUSTNADO that develops along the initial edge of a gust front. You know, if you've been outside, you see the thunderstorm coming, and all of a sudden it gets a lot cooler. Well, sometimes along that gust front, you can have what we call a GUSTNADO, and we'll take a look at all those things. And I may actually have to stand up and point at the wall. I'll do whatever I can to tell you what's going on. Okay, so the very, very first thing, you can never have a tornado if you don't have surface moisture. Now, we've got this bathtub not too far away, about 150 miles. It's the Gulf of Mexico, and that usually supplies us with plenty of surface moisture. You know, you've heard us talk about relative humidity, about dew points, and anytime you have dew points, I would say, kind of rule of thumb, over 55. That's sufficient for thunderstorms. Anything less than that, and it's hard without a lot of other processes we won't get into to produce thunderstorms. So anyway, we need the low-level moisture. That way you can have the clouds that will develop through cooler air aloft, and that moisture is actually kind of a way to think of it. It's kind of like a propellant that helps lift the clouds and lift the thunderstorms through the atmosphere. So you've got to have low-level moisture. Okay. Second thing is directional shear. And I know it's like, what is directional shear? I'm already getting really fancy on you here. Okay, directional shear. As you see by the little graph there, let's say as a big storm system comes in from the west, you've heard us talk about it. You've heard me talk about these upper-level systems. Okay. As they approach, if conditions are right, like right near the surface, you kind of see that arrow, kind of, let's say that's southeast. Okay, that's one direction. Just above that, at about 5,000 feet, well, you'll have a southerly wind or a southwest flow. Then above that, let's say at about 10,000 feet, then you'll have a west flow, and then pretty much that carries you all the way up to about 30, 40, 50,000 feet, okay? You'll have usually a west flow, okay? But you see how that's kind of a spinning motion already. You can kind of see what's going on. So, as these thunderstorms build through the atmosphere, they have a tendency to spin, and that's what we call the mesocyclone. Again, I'm not going to get too fancy here, but that's the main parent thunderstorm. The supercell is already spinning, okay? And that does a couple of things. But for one thing, usually when you have directional shear, and especially you couple that with speed shear, we're going to talk about in a second, then instead of the updraft being straight up and down, like let's say in a garden variety thunderstorm in the afternoon on a July afternoon, very little speed shear, very little directional shear usually, and that thunderstorm will develop straight up and down and then just collapse. Well, when you have a supercell, the thunderstorm is actually leaning like this. So you have a lot more area for updraft. The thunderstorm is usually longer lived, and the whole system just kind of works better. So, two topics. One, you need moisture. Number two, you need directional shear. Okay, let's see, we got a couple of questions here already, but I'll get on a roll here. Anyway, Amy, how are you? First grade. First graders in the house. How are you doing, first graders? Hopefully you watch in the mornings. And James, let's see, you're exactly right. We're just talking about that. And Sierra, okay. Hey, I won't, that'll be our secret, Sierra. That'll be our secret. By the way, I love Bill. Okay, let's take a look. So we've got moisture. We've got also some directional shear. Now you've got to have speed shear, okay? And again, I'm getting a little fancy here, but as you see my little graphic, this is going to do a couple of things. One is usually when a storm system approaches and we've got, let's say we're in a marginal risk or a slight risk or even an enhanced risk for severe storms for the day, yeah, it'll get breezy at the surface. I mean, you know, usually it's about 20 miles an hour, something like that, maybe 25, maybe even 30 miles an hour. But usually when it's 20 miles an hour near the ground where we live, boy, just above that, especially if you get away from the planetary boundary layer. And what I'm talking about when I say planetary boundary layer, it's usually within about 5,000 feet. You've got buildings, you've got trees, you've got all kinds of stuff, and that adds a little friction. So that kind of slows down the wind flow. But just above that planetary boundary layer, boy, everything just runs really smooth and you have lots of wind. It's a lot of times when you get in an airplane and you take off out of the airport, of course these days it seems kind of foreign for, anyway. You take off out of that airplane at the very beginning, I mean it's bouncy and it's really bumpy and that's because of all the friction close to the ground. You get up over about 5,000 to 6,000 feet, all of a sudden it gets a lot smoother. Now you can run into some turbulence, but that's something else. But anyways, we take a look at our speed shear. Notice what's happening. When a storm system approaches at the ground, it's about, again, 30 miles an hour, but above that, I mean, you could see winds at 50 miles an hour, about 6,000 feet, and a lot of times at 30, 40,000 feet, you're talking about winds at 100, 120 miles an hour. So you see what happens there. This is what we call streamwise vorticity. The atmosphere is invisible. It would be so awesome if there were some kind of glasses or something we could use and see what the atmosphere is doing as these storm systems approach and we have the chance for tornadoes. Because what you would find is in the atmosphere you'd have a lot of this kind of motion like a pinwheel, okay? And it's really broad, really big, like big kind of huge pinwheels kind of, okay? Well, when you get these thunderstorms that develop, it'll tend to lift those pinwheels and then tighten them up, and that's kind of how we get tornadoes. I'm getting ahead of myself. So we got moisture, we got directional shear, and we've got speed shear. I hope all this is making sense to you so far, because this is pretty complex that we're talking about, pretty complex situation here. Okay, fourth thing and the last thing is you need some kind of dynamical lift in the atmosphere. Here's our upper level system approaching, our little trough adds lift in the atmosphere, okay? So if you're evacuating mass and you're lifting it up, well, you're going to cause low pressure at the surface and kind of like a focus, all right? So you need that lift as well. So moisture, directional shear, speed shear, and you need lift. You have all those, hey, you've got the makings of what could possibly be a tornado. Now you need the thunderstorm, of course. Susan, how are you doing? Hopefully you're doing okay. I saw a water tornado. I saw a water spout at Port Mansfield. You know, I tell you what, being along the coast is so cool. I'll never forget. I was down at Key West one time, and water spout was not very far away, but they're just the coolest things to watch. And the winds can get pretty strong, 50, 60, 70 miles an hour, something like that. And so Flora, okay, Flora's who I'm talking to. Yeah, pretty cool there, Flora. All right, so we've got those four things again. That's what you need for a tornado to develop. But we need a thunderstorm, okay? So I bet you didn't know this. A lot of times in a thunderstorm, even on the hottest summer day, it could be 90 degrees, 95, it could be 100. But somewhere around, 18,000, 15,000 feet, anything above that is below freezing, okay? But you didn't know that. If you look at a thunderstorm in the spring and the summer, more than half of it, or about half of it, is made out of snow and ice, okay? So temperatures below freezing up above. That's how, of course, that's how we get hail with strong updrafts and so forth and so on. But anyway, so we have this thunderstorm that develops. We've got enough moisture in place. That moisture is propelling that thunderstorm up through the cooler atmosphere above, okay? So it's almost like a hot air balloon, okay? As long as the parcel of air is warmer than its surroundings, it will continue to lift, and it'll go all the way up. Matter of fact, it'll hit the roof of the atmosphere, and then a lot of times when you see those mimosas clouds that are kind of puffy on the bottom sides when it's really unstable and really stormy outside, it's because that thunderstorm has hit the roof of the atmosphere and still wants to grow, fanned out, and then kind of building on the bottom side. That's mimosas cloud. So anyway, so we have this thunderstorm that grows because of the moisture. We've got the directional shear in place, so the whole thing is spinning. The mesocyclone, the core of it, is spinning abound, and you've got that speed shear as well. That really helps, especially way above. It helps to evacuate the mass, because can you imagine the amount of water and the amount of snow and the amount of moisture you have in that thunderstorm? If it just sat there, it'd be like a garden variety storm where it lifts and then just collapses. But in the springtime, usually here in South Texas, springtime, sometimes in the fall, boy, you have this system that develops where you have that mesocyclone that really cranks and it's tilted updraft, and a lot of that moisture and everything is kind of evacuated at the top. That's why you get those big long anvils, okay? And then you have the speed shear and everything kind of come together. So I showed you the speed shear with the streamwise vorticity, those little things that kind of spin like this. Well, as that thunderstorm grows, well, sometimes it'll lift the vorticity up, kind of zipped in place. It's kind of hard for me to show without a radar. But anyway, that's the way you build a thunderstorm. That's the way you build a possible tornado. So this is what I was going to show you right here. As you take a look, this is what I was getting at, is you have that kind of streamwise vorticity. It's lifted up into that parent mesocyclone. And have you ever seen like a skater on the ice skates? This will show my age a little bit. Dorothy Hamill. I don't know. I wasn't going to bring up Tanya Harding. Well, anyway, so you got the skater out there, and the skater's got the arms way out and spins kind of slowly, right? Well, as they draw everything in, well, then they go faster and faster. Weather school, what do we call that? Conservation of momentum or something like that. Anyway, so it draws in closer and closer, and you go faster and faster and faster, and that's and then when you stretch that column, well, it makes it go faster and faster and faster. And so that's basically how a tornado is formed, okay? Let's see. Okay, now we're getting to another part. So that's your most common, that's kind of your supercell mesocyclone. That's your way to get tornadoes, and we have different stages. You know, one thing I forgot is I forgot to put the stages, okay? You got EF1, EF2, EF3, EF4, EF5, okay? Usually here in South Texas, most of our tornadoes are EF0, EF1s, EF2, okay? So EF0, less than 100 miles an hour. EF1's a little bit more than 100 miles an hour, which is nothing to shake a stick at. I mean, I've been in 5 hurricanes, and most of those winds were around 110 to 120. So EF1, EF2, a little bit stronger than that. That's the bulk of our tornadoes here in South Central Texas, especially here in Bear County. We rarely, I mean, I think EF3 maybe is the strongest we've ever had, and very few of those. I don't think we've ever had an EF4 or EF5 here in the county, okay? Jarrell, Texas is one of the furthest south EF5s, if you know where Jarrell is. You know, if you're going to Dallas, Fort Worth, and you pass Austin, and I think it's just before Georgetown or just after Georgetown, there's Jarrell. And that was way back like around 99 or something like that. So we just don't see those big monster tornadoes here in Bear County. So all the first graders, all you elementary kids, you can sigh of relief. We don't have those big ones that'll just bust down and, you know, bust down the house. Now, I've got family that lives in Mississippi, in Louisville, Mississippi. And I'm kind of getting off the subject a little bit, but we've got a little time here, I think. Louisville, Mississippi, and they had an EF4 tornado, and not very far from my mother-in-law's house, and amazing. If you've ever seen what an EF4 tornado can do, it is totally amazing. Because where they live out in the middle of the forest. The pine trees there are probably 75 feet tall, big pine trees. There was a swath just right on the outskirts of Louisville, Mississippi. She lives right on the outside. I'm not kidding you. It's probably a quarter mile wide, maybe even a little bit wider than that. Probably about a quarter mile. and all of those pine trees were snapped about, 7 feet from the ground. All looked like matchsticks. It was amazing, and the houses, the only thing that was left was the very, very center of these houses that were in the path of this tornado. So if a tornado comes your way and there's a tornado warning, we tell you to seek shelter, smallest part of your house, the lowest floor of your house, you want to put as many walls around you as you can. So the middle part, smallest part of that, smallest room in the house on the lowest floor. Do not be on the second floor. But it was amazing. These houses, the only thing that was left was a little room right in the center. Everything else was gone. Boards into pools down below ground. It was just an amazing thing. But she lives right on the outskirts of where that tornado hit. Matter of fact, there were wheelbarrow handles that were in the house, and stuff. It's just an amazing what these big, huge tornadoes can do. So good thing here we don't see those kinds. So anyway, told you I'd get off the subject a little bit, and I did. Okay, Susan, how are you doing? And Flora, how are you? Okay, so we're going to talk about, okay, are landspouts and dust devils, are they the same thing? No, they're not. Landspouts are completely different. You know what? We're going to talk about that here in just a second. So that is good. And Amy, how are you doing? All right. So landspouts, and we're going to add at the very end. We'll add dust devils in. Okay. Landspouts. How do they form? Well, and this gets to my little pet peeve here, because, well, let me talk about it, and then I'll get to my pet peeve. All right. So landspouts. When you have that thunderstorm that I showed you earlier, and it develops very rapidly, well, a landspout will develop kind of from the ground up, which is the opposite kind of situation of a full-fledged tornado from a supercell. And usually from a landspout, one way you'll know that it's a landspout instead of a tornado is it won't have the typical wall cloud, won't have the whole beaver's tail and the whole thing that usually comes with a regular supercell thunderstorm. So the landspout, and it develops much like a waterspout. You have these thunderstorms that develop, and they develop really rapidly, okay? So let's say you've got a boundary that's left over, maybe a stationary frontal boundary or some kind of a boundary where the air is already kind of spinning anyway. Well, as that air is kind of spinning and that thunderstorm grows, it'll kind of stretch it and help to stretch that column, and that column will spin faster and faster and faster. You know, these landspout tornadoes don't get that strong, but they can get up to 80 miles an hour or so and do some damage. So landspouts are created different than the whole mesocyclone kind of a thing with the regular tornado. So that's a landspout. Now, a waterspout, they look very similar too. So you've got a waterspout, you've been out the coastal sections, you see these big thunderstorms and they build very rapidly, a lot of upward motion, and from the ground up basically these waterspouts will form. Sometimes they'll form from the clouds down too, but either way it's from stretching of that column of air that is probably already spinning anyway, okay? So a totally different way waterspouts develop from regular tornadoes. Now here's my pet peeve, now we'll get to it. A lot of times people will say there's a big supercell thunderstorm and it goes over the water and a tornado forms. Well, that's a tornado over water. That's not a waterspout. That's a tornado that's developed the good old-fashioned way from a supercell thunderstorm, and bam, that's over water. Too bad. Still a tornado. Now, and then sometimes there'll be kind of the opposite situation where there'll be like a waterspout that goes onto the land. Well, still a waterspout, became a tornado on the ground, but still developed a different way. So anyway, I got to my little pet peeve. I got it off my chest. Now we'll go on to GUSTNADO, and then we'll finally hit the dust devil like we wanted to here. Okay, Susan, I think, is the one that asked for that. All right, so GUSTNADO, how does that happen? Well, we talked about tornadoes, we talked about landspouts, and now we've got GUSTNADOs, which really is kind of interesting, because what will usually happen from a thunderstorm, you have that cool air that kind of rushes out, the rear flank downdraft or just whatever. So you got that cool air that comes from it, and a lot of times there'll be a rising motion where that warm air is feeding into the thunderstorm, and you'll create some spinning, okay? Well, in a GUSTNADO, you won't have any connection to the base of the thunderstorm and the ground. It's basically 30 feet high, maybe as high as 300 feet high, pretty low to the ground, but you'll have a gustnado, and sometimes they can get a little strong right there on the leading edge of the gust front, and that's why we call it a gustnado. I think, do I have one more? Yeah, here's another way to look at it. So you've got that warm air that's rising into the thunderstorm, cool outflow, you got spinning, and if it spins very fast, it'll start picking up debris, so forth and so on, and you'll see it. It's what we call a gustnado. No condensation funnel from the cloud, just kind of out in advance of the thunderstorm sometimes, kind of all by itself, and that's the gustnado. By the way, a lot of times when there's a tornado, a lot of folks won't call it a tornado because the middle part is invisible. A lot of times it's like that. You'll see like the little, you'll see the funnel cloud from the base of the thunderstorm, and then the part's invisible, and then at the bottom, you'll have just debris on the ground. You have maybe some dust. Well, that's a tornado on the ground. You just can't see it. The condensation funnel is just invisible. A lot of times if it's had a heavy rain and there's not a lot of dust, then middle part of that tornado, you won't be able to see it. Most of the time, though, there's enough dust and debris and stuff that you'll see that whole condensation funnel and the whole thing down to the ground. So anyway, now getting to dust devils. Well, that's really interesting. That's not really related. I guess it's really not related to anything that a tornado, because it's not a gustnado, not a landspout. The whole process is kind of different. What happens when you see a dust devil is you have uneven heating of a surface. A lot of times it'll happen on a field, like a field that doesn't have a lot of grass or pavement. A lot of times, kind of uneven. So what'll happen is on a summer day, especially if the winds are really light, well, you'll get that pavement that's really superheated, and all of a sudden pressure will be a little lower there, and so bring in air from around, and it'll move in. And if the situation is strong enough, that dust devil can get pretty big. So the dust devil originates at the ground, and it's from uneven heating of surfaces. That's how you get the dust devil. So it's not really related to tornadoes or anything at all. So anyway, I'm not really sure how long I've gone. Let's see, how long have I gone? Oh, wow. Okay, we've gone quite a ways. We've gone almost 25 minutes already. Anyway, hopefully I haven't bored you to death with my talk about tornadoes. Like I said, you know, I'm not the best teacher in the world. Anyway, not the best teacher in the world. But anyway, hopefully you learned something from that. Hopefully it was very educational for you. So just to kind of recap, 4 things you need moisture, surface moisture, low-level moisture for sure. The middle part of the atmosphere, most of that can be dry. Okay? But if you have that low-level moisture in the planetary boundary layer in the lower 5,000 feet, that's golden. Then you have directional shear. You need to have some speed shear. And you need to have some kind of lifting. You have those things, you got a chance for a tornado. And I guess that's what we're here for, to tell you when that is definitely possible. Okay, so let's take a look at the forecast. It's Mother's Day weekend coming up. We've got cloudy skies outside. Really interesting situation going on right now. The warm frontal boundary is camped across, it's moving northward, but pretty much like across the northern part of the county. There's a good part of the hill country where temperatures are still in the 70s, but south of this warm front, temperatures have jumped into the 80s already. Let's take a look, and it shows up very nice on the visible satellite imagery. I love the visible satellite, especially in the noon hour. You notice where the skies don't look real blotchy, looks kind of solid. Well, that's where we have that blanket of clouds there. South of that, where the sun is penetrating through and you've got some kind of vertical motion, well, that's where those temperatures are the warmest, where it looks like little cotton balls down in Frio County, Atascosa County, southern Bexar County, down towards Wilson County, and it is making a difference as far as the temperatures are concerned. Pleasanton's at 82, while Bernie is only at 72, Fredericksburg's at 71, and then you go further south and look at those temperatures. Down at Creasle Springs, it's 86, Catula's in the mid-80s, down at Beeville, already 88 degrees. And so we're going to continue to see southerly winds. We're going to see a little sunshine. It's still going to be mostly cloudy. And I think this morning I went with a high of 86. That still seems very reasonable for the rest of the afternoon. So as we head through the rest of the afternoon, the winds will get breezy. I think 10 miles an hour to 15, and then increase into 15 to 20, and then we may have some wind gusts up to 25, 30 miles per hour or so. And then as we head into tomorrow, We'll have a southerly wind to begin the morning. I think tomorrow morning is going to be humid. And then winds will shift around to the north. And look at that. You can see that cold front coming through. And tomorrow, it'll be breezy in the afternoon, but from a different direction, from the north. We'll have some of those winds, again, 15 to 20, some gusts a little bit higher than that. So let's take a look at the surface map across the state. We've got high pressure over around Mississippi and Alabama. We've got lowering pressures out to the west. I drew this map, I don't know, it's been several hours ago, so it's a little outdated. If I had to redo this map again, I'd put an L instead of Colorado. It'd be just like west of Amarillo. And then I'd have almost like a dry line down towards Eagle Pass and Midland, it looks like, because they're almost at 90 degrees there. But either way, lowering pressures across the western part of the state. To the east towards Mississippi and Alabama, you've got high pressure. We're kind of caught in between. And so especially with just a little sunshine, we'll have gusty winds as we head through the rest of the afternoon, I think. So dew points, one of the ingredients that I talked about earlier. By the way, we're not going to have any tornadoes, and I doubt we'll even have a lot of thunderstorm activity. But anyway, moisture is going to be on the increase. We'll see those dew points by tomorrow morning in the upper 60s. But the way the upper level pattern is set up, we have no real upper level support, so very little chance for rainfall with this front coming through, and then it'll dry us out. And then behind the front, our temperatures are going to be way below average. It's going to set us up for a real decent Mother's Day weekend. It's going to be a treat for the mothers. It's a gift for the mothers out there. So as we head through the day today, again, notice how the clouds, even in Bexar County, get a little splotchy, so that means a little sun shining through. Maybe an isolated shower, but don't count on it. Temperatures in the mid-80s, down to the south and southwest above 90. And then tomorrow morning, we'll be looking at low temperatures in the lower 70s, okay? Lots of cloud cover, but because we just don't have a lot of upper level support, this front's having to fend for itself. I mean, look at that, just very, and we need some rain. Our aquifer's dropping about a foot a day now. But look, I mean, just doesn't look very good. This is just one computer model, but most of them are like this, real skimpy on rain. I mean, I'd be surprised if we picked up a few hundredths of an inch with this frontal boundary pushing through. And then temperatures drop behind the front, and by Saturday morning, you know what, Saturday morning we could pick up a few showers, maybe a few thunderstorms south of the area, south of Bexar County, and I think temperatures will start off in the upper 50s for Saturday morning. So that'll be nice as we head into Saturday morning. Take a look, go through there. All right, here's the 7-day. So for today, 86, kind of mostly cloudy. You may have a few breaks of some sun, breezy. Tomorrow, 70 for a low, high of only about 82, because I think this front's going to come through around midday, and there is some cool air behind this front. A lot of the northern part of the country, eastern part of the country is going to get pretty chilly. Front moves through, slight chance for a shower into Saturday morning, and then Saturday mostly cloudy. High temperatures in the mid-70s, around 76. And then on Sunday, Mother's Day, it's going to be a treat, I'm telling you. Low temperature 56, high temperature around 82. Nice day, partly cloudy skies. So just for Mom, just for you moms. By the way, if you're a mom, thanks for being a mom. I want to say Happy Mother's Day to my mom. Hopefully she's watching. Anyways, we head into Monday, 20% chance of rain, high 84. 30% chance of showers and storms on Tuesday. And then Wednesday, I could have thrown in a 20%, but it looks like the cap is going to be too strong probably. So just partly cloudy and 88 degrees for your high on Wednesday. All right, let's see if we get any last questions here. If the dust devil spins clockwise, they were good spirits. Oh, yeah, if dust devils spin clockwise, they were good spirits, and counterclockwise, bad spirits. I guess it's a old wives' tale, I think. Let's see. Looking from the Caribbean, yeah, when I was down there at Key West, exactly. Let's see. Was the computer modeling episode. I didn't have the what I call the syllabus. I didn't have that in front of me. I don't know, did we miss that one day? Maybe we did. I don't know. I know Thursdays is usually my days, but, oh, that was supposed to be yesterday. And I guess so. I don't know what happened to the computer modeling. I'm not even sure who was supposed to do it yesterday. I'll find out. And but that is cool that you guys know what days, what's coming up on the day. And I probably should. I just know, like I said, I just take care of Thursdays, so I know what we're doing today. And hopefully you learned something today about tornadoes. It's kind of a brief lesson. We could get really deep into it, but you probably don't want to. But we do appreciate you watching KENS 5. I know I do. Thanks for watching in the mornings. Thanks for watching at noon, and also watching Bill in the afternoon, and Megan and Andrew there on there as well. And we will see you, at least I will see you tomorrow morning, but definitely watch this afternoon. And again, thanks a bunch. Appreciate it. We'll see you later.